Today we are going to discuss next point of real analysis, Cauchy sequence. What is meant by Cauchy sequence? So Cauchy sequence. Okay. Cauchy sequence. Definition of Cauchy sequence is if sequence Sn is said to be Cauchy sequence is said to be Cauchy sequence if for all epsilon greater than 0 there exists any positive integer n belongs to set of index set or set of natural number or set of positive integer such that the distance between any two number Sm means nth number of sequence and Sn means nth number of sequence Sn. Okay, and their differences must be epsilon. Epsilon is any positive integer. Okay, this is very small or whatever may be, but their distance is very less than epsilon, where epsilon is greater than 0, and for all m and n are greater or equal positive integer n. Okay, so this is our definition of Cauchy sequence. Suppose that how to find the how to show given sequence is Cauchy sequence. Okay, so for that here for example show that sequence 1 upon n. Okay, sequence is given that 1 upon n where n runs from 1 to infinity is Cauchy sequence. Show that sequence 1 upon n is Cauchy sequence. So how to showing that for Cauchy sequence, to show that their distance mth number and nth number, any two number mth number and nth number, their difference is a very small. Epsilon is very small or whatever may be, but their difference is must be less than epsilon. Okay, epsilon is a positive integer any. Okay, distance is always considered as in positive term. Okay, so therefore here to show that Sm and Sn is a sequence, their distance is less than epsilon, that is mod Sm minus mod Sm minus Sn is less than epsilon. So here let sequence Sn n runs from 1 to infinity is equal to sequence 1 upon n where n runs from 1 to infinity. Therefore Sn is equal to 1 upon n and Sm is a 1 upon m. This is a nth number, this is mth number. Okay, this is mth number. So let epsilon greater than 0 be given. Suppose that okay be given, then consider mod Sn minus Sm minus Sm minus Sn is equal to, put their values 1 upon m minus 1 upon n. This is can be written in the form of 1 upon m plus of minus 1 by n. Okay, this is minus 1 by n can be written in the form of minus plus minus we get, and therefore this is equal to, using this result, mod a plus b is less than or equal to mod a plus mod b. Using this result this can be written in the form of mod 1 upon m plus mod of minus 1 by n, and this is can be written as mod 1 upon m plus mod 1 by n, since because minus 1 by minus a, mod of minus a is equal to mod a, that is which can be written as mod minus 1 into a, and mod minus 1 into mod A is equal to mod E. Okay, in this way, therefore sorry, this is less equal. Okay, this is less equal and this is equal to for our term. This is less equal for this term. Okay, and therefore mod Sm minus Sn is less equal 1 upon m, mod 1 upon m plus mod 1 by n. And here we have to show that this term is less than epsilon. Okay, for all n, for all mn greater equal n, here one of the number is exists such that for n, m and n are greater equal positive integer n. Okay, so for that here consider let m and n are greater equal n, m and n greater equal n, which imply that m is greater equal n and n is also greater equal n. Okay, then 1 upon m is must be less equal 1 by n, because 2 greater than 3, then 1 by 2 is less than 1 by 3. Okay, in this way m is greater equal n, then 1 upon m is must be less equal 1 upon n, and here also 1 upon n is must be less equal 1 by n, which imply that mod or 1 by m plus 1 by n. Okay, 1 by m, here 1 by m plus 1 upon n is must be less equal 1 upon n plus 1 upon n, which is equal to 2 by n. Therefore 1 upon m plus 1 upon n is less equal 2 by n. Okay, which is less equal 2 by n, and therefore here take their values which is less equal 1 upon m plus 1 upon m. This mod taking deleting mod, then we get a values mod of 1 by m is equal to 1 by n, and mod 1 by n is equal to mod 1 by n. Okay, 1 upon m plus 1 upon n, and their value is this value, and this value is less equal 2 by n. This value is less equal 2 by n. Therefore mod Sm minus Sn is less equal 1 upon m plus 1 upon m, and this is must be less equal 2 upon n, which implies that mod Sm minus Sn is must be less equal 2 by n. Therefore, but we have to show that given sequence is when Cauchy, if this distance between m term and n term is less than epsilon, so we have to find the if we choosing n, this n, if we choose this n is strictly greater than 2 upon epsilon, then epsilon is strictly greater than 2 by n. Okay, then or 2 by n is strictly less than epsilon. Okay, so therefore if we choosing n is greater than 2 upon epsilon, then epsilon is greater than 2 upon n. Therefore mod Sm minus mod Sn is less equal 2 upon n, and this is strictly less than epsilon for all nm greater equal n. Because why? Because this n is choosing from this. Okay, m and n are greater equal n, and n is strictly greater than 2 upon epsilon, and therefore mod Sm minus Sn is must be less than epsilon for all nm greater equal n. Okay, this is our, and therefore sequence Sn satisfies this condition. Therefore by definition of Cauchy sequence, by definition of Cauchy sequence, sequence 1 upon n where n runs from 1 to infinity is Cauchy sequence. In this way, how to prove given sequence is Cauchy sequence? Then difference between two term, difference between m term and n term is less than epsilon for all m n greater equal to n. Then we say that given sequence is a Cauchy sequence. Okay. Similarly, next example, suppose that show that. Okay. Show that take any sequence. Suppose that n minus 1 divided by n plus 1. Okay, n minus 1 divided by n plus 1 is Cauchy sequence. How to show this Cauchy sequence? So by definition we have to show that mod Sm minus Sn is less than epsilon. Okay, so let sequence Sn where n runs from 1 to infinity is equal to n plus 1 where n runs from 1 to infinity n plus 1 divided by n minus 1 divided by n plus 1 where n runs from 1 to infinity. Therefore Sn is equal to n minus 1 divided by n plus 1, and then Sm is equal to m minus 1 divided by m plus 1, m minus 1 divided by m plus 1. Okay, so let similar process, let epsilon greater than 0 be given, let epsilon greater than 0 be given. Suppose that, then consider mod Sm minus Sn is equal to, put their value, Sm is m minus 1 divided by m plus 1. Okay, minus n minus 1 divided by n plus 1. So solve this mod. So here denominator is not same, so multiply this by n plus 1 and multiply this by m plus 1, and solving this, take denominator same, we get suppose that n plus 1 into m minus 1 minus n minus 1 into m plus 1 divided by m plus 1 into n plus 1. Okay, so therefore multiplying each term, then nm minus n plus m minus 1 minus nm minus nm then minus n, then minus plus there minus plus m, and then minus 1 plus 1. Okay, minus 1 plus 1 in this way, divided by this term as it is, m plus 1 into n plus 1. Okay, so solving this, plus nm, this get cancelled, remain only minus n minus 2n, and m plus m 2m, this one get cancelled, 2m minus 2n divided by m plus 1 into m plus 1. Okay, in this way, so 2 get 2 into m minus n divided by m plus 1 into m plus 1. Okay, and then we get taking 2 is positive, so taking in outside of mod, 2 into m minus n divided by m plus 1 into n plus 1. Okay, m plus 1. So converting this term to this term. So how to convert this? Only rearranging these equations. So therefore mod Sm minus Sn is equal to mod Sn minus Sn is 2 into adding 1 and subtracting n minus 1, adding and subtracting 1, we get m plus 1 into n plus 1. Okay, therefore 2 into, this is m plus 1, this is m plus 1, taking minus sign is common, remaining only n plus 1. Okay, in this way m plus 1 into n plus 1. Okay, so which is equal to dividing each term by separately, we get m plus 1 divided by m plus 1 into n plus 1, remaining only minus m plus 1 divided by m plus 1 into n plus 1. Okay, in this way remaining only term 1 upon n plus 1 minus 1 upon m plus 1. Okay, therefore this value is for SA minus SN, and we have to show this value is strictly less than epsilon. Okay, so for considering in this way, if we choosing here, if we let mn are greater equal n, which implies that 1 upon m is less equal n, 1 upon n, and 1 upon n is must be less equal 1 upon n, which implies that for here m is greater equal n and n is greater equal n, and using this 1 upon m is less equal 1 upon n, 1 upon n is less equal 1 upon n, where this n is any positive integer. So which implies that 1 upon m plus 1 1 upon m plus 1 is must be strictly less than 1 upon m, and which is less equal 1 upon n, and 1 upon n plus 1 which is must be strictly less than 1 upon n, and this 1 upon n is less equal 1 upon n. Therefore 1 upon m plus 1 is strictly less than 1 upon n, and 1 upon n plus 1 is strictly less than 1 by n. Therefore suppose that this equation is star equation. Okay, mod Sm minus Sn. Therefore 1 upon, therefore here 2 into mod 1 upon n plus 1 minus 1 upon m plus 1 is equal to this written in the form of 2 into 1 upon n plus 1, which is less equal, okay, less equal, plus mod 1 upon m plus 1, and which is less equal 2 into 1 upon 2 into 1 upon n plus 1 plus 1 upon m plus 1 in this way. Okay, so therefore equation star becomes mod Sm minus Sn. This equation star Sm minus Sn, their value is less equal 2 into 1 upon m plus 1 plus 1 upon n plus 1. Okay, in this way suppose their equation is 1. Therefore from equation 1 1 upon m plus 1 plus 1 upon n plus 1, their value is must be strictly less than 1 upon n plus 1 upon n, because 1 upon m plus 1 is less than 1 upon n, and 1 upon n plus 1 is less than 1 upon n. So this is equal to 2 upon n, and therefore 1 upon m plus 1 plus 1 upon n plus 1 is must be strictly less than 2 upon n. Okay, 2 upon n. Therefore equation 2 becomes, suppose that this equation 2, okay, this equation 2 becomes mod Sm minus Sn is strictly less than 2 into this value is less than 2 by n. Put their value is 2 by n, which is equal to 4 by n. Therefore mod Sm minus Sn is strictly less than 4 by n. Okay, therefore if we choose n is strictly greater than 4 upon epsilon. If we choose n is strictly greater than 4 upon epsilon, then epsilon is must be strictly less than 4 upon n, that is 4 upon n is less than epsilon. Therefore equation 3 becomes mod Sm minus Sn is 4 upon n is less than epsilon, is epsilon for all n and m greater equal positive integer n. If we choose n is strictly greater than 4 upon epsilon is positive, so n is must be choose greater than 4 upon epsilon. Then for all values of n and m, the distance between sequence of two number, that is mth number and nth number, is must be less than epsilon. So in this way, find the how to show given sequence is Cauchy sequence. Okay, so this is some examples. Then next example is theorem. Okay, every convergent sequence of theorem on Cauchy sequence. Statement is every convergent sequence of real number, is Cauchy sequence. This is very important theorem. Every convergent sequence of real number is Cauchy sequence. Okay, any convergent sequence of real number, every convergent sequence of real number, not for other number, real number, rational number, whatever may be, but for real number, every convergent sequence, if sequence is convergent of real number, then which is a Cauchy sequence, that is which satisfy this condition. Okay, every convergent sequence. So proof of this, firstly given that what are given sequence is Sn be a sequence of real number and which is convergent, and to show that convergent sequence Sn is Cauchy sequence. Okay, let sequence Sn n runs from 1 to infinity be a sequence of real number, which is convergent, and suppose that they has limit L. If sequence is convergent, then it has a unique limit, and we say that which is a convergent and converges to L. Suppose that given sequence has limit is L, and therefore that is limit n tends to infinity, Sn is equal to n, and therefore by epsilon n definition, for all epsilon upon 2, for all, here epsilon choose this is constructive for if we choosing epsilon by 2 greater than 0, here any positive number exists, n belongs to I, such that given sequence satisfies Sn minus L is less than epsilon upon 2. Sn minus L is less than epsilon upon 2 for all n greater equal n. Okay, this is equation number 1, suppose that. Okay, now m and n, suppose that greater equal n, then mod Sm minus Sn, consider. Okay, here suppose that consider mod Sm minus Sn. Mod Sm minus Sn is equal to adding and subtracting L in this term, Sm minus L minus Sn plus L. Okay, minus Sn plus L in this way. Okay, adding and subtracting L, we get mod Sm minus L minus sign here common, suppose that, and Sn minus L. In this way, taking their values, separating this mod. Okay, mod Sm minus L here they using result mod A minus B is less equal mod A mod A plus mod A plus mod B using this result. So their value is or here another result is also here positive sign minus L plus L. In this way mod minus Sn plus L, okay, in this way, and therefore which is less equal mod Sm minus L plus, take here minus sign is common, minus 1, then remaining is Sn minus L, okay, and which is equal to mod Sm minus L plus mod of minus 1 into mod of Sn minus L, okay. So in this way here all are equal to for this term, okay, this all are equal to for this term equal to mod Sm minus L plus their mod is 1, remaining only Sn minus L, okay, and therefore mod Sm minus Sn is strictly less equal mod Sm minus L plus mod Sn minus L for all n m greater equal n, okay, for all n m greater equal m, but their values Sn minus L is strictly less than epsilon upon 2. Similarly if we taking n by m, okay, if then Sm minus L, this sequence, this is also sequence of given sequence, okay. So this term is also less than epsilon upon 2 in this way, from 1 Sn minus L is less than epsilon 2. Similarly Sm minus L is also strictly less than epsilon upon 2, okay, from 1, okay. So therefore which is equal to epsilon upon 2 plus epsilon upon 2, which is less than epsilon, which is equal to epsilon. Therefore mod Sm minus Sn is strictly less than epsilon whenever n and m are greater equal n, and therefore given sequence Sn is a convergent sequence, and this Sn convergent sequence satisfies this condition, that is m distance between two terms of given sequence is less than epsilon, okay, and therefore given sequence Sn where n runs from 1 to infinity is Cauchy sequence, okay. This is very important theorem for university exam. How to proving this theorem? Firstly, given that every coordinate sequence of real number, okay, Sn is given that consider Sn is any sequence of real number and which is convergent, which implies that it has limit L, okay. Suppose that it has limit L, given sequence is convergent and it has limit L, then we satisfy epsilon n definition, okay, therefore by epsilon n definition, if we taking epsilon this term for all epsilon upon 2 greater than 0, okay, for all epsilon by 2 greater equal 0, then here any one of the number is exist positive integer such that we satisfy this condition, mod Sn minus L is less than epsilon upon 2, and consider Sm minus Sn, and then rearrange only and take their values strictly less than epsilon upon 2 plus epsilon upon 2, and epsilon upon 2 plus epsilon upon 2 is equal to epsilon. Therefore mod Sm minus Sn is less than epsilon for all n greater equal n, and therefore this sequence Sn satisfy the condition of Cauchy sequence, and therefore given sequence Sn is a Cauchy sequence. So